Welcome to the Alpha Training and Consulting's online training program. Today's module is entitled Application Module 3, Reducing Sigma to Save Money module. The purpose of this module is to help students understand how reducing standard deviation saves money in both raw material and inventory costs. And when it comes to these application modules, I take the things that I think are very most important and I put them in these application modules. Now, you've already had this module and listened to this module back at the very beginning. It was entitled Fundamentals and Project Selection. So I'm going to switch over to an older recording, but this is the objective, the new objective. And so you've probably heard it before, but this will be a reminder. Remember, this is supposed to make you more powerful at being a Six Sigma black belt, Lean Six Sigma black belt. So listen to this, understand it, memorize it, and if you're taking the GSIP certification exam, memorize it because there's a good chance this is going to be on the certification exam. So it's extremely important. All right, number 3 is the next project, Decreasing Raw Materials. This is a little more difficult. This project allows the organization to use fewer raw materials such as paint, solder, and other applicable raw materials through variability reduction. Sounds like a solution 3, doesn't it? On a scale of 1 to 10, with 10 being the most difficult project and 1 being the very easy project, I would rate this one at a 9. So this is going to use all your skill sets that you get from the black belt training. You could do it as a green belt also, but usually it's a black belt project. Decreasing raw materials. In project 3, the student will gather data on all perceived critical variables within the scope of the project. That sounds familiar. With this data, the student will perform various design of experiments that will ultimately tell the student what the optimal process settings are in an effort to reduce variability. So this is a solution 3. We're reducing variability. So here it is. Let's say you're painting a part. So we slap some paint on there. Maybe it's a powder coat process, let's say. And that powder coat paint can be rather expensive, is what you'll find. And this red line is the lower spec limit. If we delve below that lower spec limit line, then of course we're going to have scrap. So we don't want to do that. Of course, there's always risk, because I don't know if I've told you this yet. I draw this normal distribution as it ends right here. In reality, it's a continuous curve, and it never touches that horizontal line, which tells us what? There's always going to be a probability that we could violate lower spec. In this case, let's say, for example, the customer says, or you do an initial analysis on the current process, and you do, and by the way, you could do that using this program, remember. So you could come back and use this program, and you may not use the whole thing. Now you're just using one sheet, and you put in the paint thickness there, and it will come back and calculate the probability of failure, and in this case I'm saying it was 1%. So we're just assuming that the scrap from this program, we use the program, and it said, listen, you have a 1% chance currently of violating the lower spec limit on this part, which isn't good, because then it'll go out in the field and prematurely experience corrosion problems. So that's where we're at, 1%. So you go to the client and say, hey, you're currently at 1% risk of violating lower spec limit. Are you all right with that? And they say, you know, we are. We haven't had that many complaints, so we want to keep that same risk level. And you say, okay, not a problem. So then you go out and you run an experiment on this paint booth, and you put the baffles in different places, you change the voltage, you change, you're just changing things, and you run an experiment. It's called design of experiments. That's the last part of the course, by the way. And you figure out the optimal process settings, and you reduce the variability of this paint thickness. Well, look what's going to happen now. You maintain the 1% risk, but on average now you maintain the same risk, but since you have lower variability, look what happens to the paint thickness. Now you can reduce the average paint thickness from this to this. while maintaining the same risks that they had before. Well, I did this project on a paint project, and out of one paint booth it saved $800,000 a year in raw materials. Imagine that. That's a lot of savings. And they had several paint booths. Now, obviously, what they should have done, I don't know that they did, but they should have implemented the same strategy on the other paint booths, and next thing you know, you're saving a couple $1,000,000 a year in what? Raw materials. That's hardcore savings there, my friends. So that's a good thing. So that's how you do that. Solution 3 can save you a lot of money in raw materials. And in this case, we said paint, but you could also, if you're cutting a part to violate, so at a given risk, you could make it a little shorter and still maintain the same risk of violating lower spec limit if you just reduce variation. So reducing variation can save a lot of money on raw materials. Why do I like to save money on raw materials? Because it's an objective savings. No one can really argue with that, and that's what I want. I don't like the projects as much where they say, well, I don't think we really saved that much, and they can argue with you without losing credibility. So the more objective, the better. Okay, so that was our third project. Now let's look at the fourth one, inventory reduction. This project reduces inventory levels while maintaining or reducing risk. And what you're going to find is it's a lot like this one, only you're reducing variability in time instead of some product attribute. Inventory and risk is reduced by reducing variability in time. It should say variability in time there in the supply chain. On a scale of 1 to 10, with 10 being the most difficult project and 1 being the very easy project, I would rate this one at a 9. This is not an easy project. It has to do with solution 3, of course. That's one reason. In project number 4, the student will gather data on all the process steps in the supply chain within the scope of the project. Now notice it's always within the scope of the project. Don't make a project so big that you can't complete it. Just keep it down, and you may test this and say, hey, it worked on these series of part numbers, and maybe it's only one part number. Okay, keep it, make the scope meet the requirements of your project. Scope means how broad, how big the project is. So you may say, I'm not going to do every part in the company, I'm just going to do part number 1035. And if it works, then I'm going to implement it to more part numbers over time. You could probably spend your whole career reducing the need for inventory. I know you could, and you'd probably get paid well for doing it, and you'd save your company a lot of money. Your salary would be they'd get a great return on investment from your salary. So with this data, the student will perform various quantitative analysis that will ultimately tell the student how much inventory is needed to support a given risk for a given standard deviation. It's a solution 3 problem. So this is a little more in depth, so put your seatbelt on, because here we go. And this is the demand. So demand is on average 100 pieces per day. So in this study, I'm going to assume that every day you have 100 pieces delivered to your shipping dock. That's the assumption. That's what's happening here. And then I do the sigma on demand. And how would you do that? You could use that spreadsheet, plug all the data in there, and see what sigma is. So, and you found that sigma was 10 pieces per day, all right? And this is on demand, which means what? Sometimes you're going to have enough raw material, and sometimes you're not. And sometimes you're going to have too much. 50% of the time you're going to have too much or not enough inventory because demand's going to be higher than you thought it would be, and 50% of the time it'll be less. Okay, so sigma's 10 pieces per day, so I'm going to fill this distribution out here. If this is 100 and sigma is 10, then this will be 110. One sigma down will be 90, and of course this 110, 120, 130, 190, 80, 70. So that's what I did. So 68.26% of the time the true demand will be between 90 pieces and 110. And 95.44% of the time the demand will be between 80 and 120. And of course 99.73% of the time the demand will be between 70 and 130 pieces. Okay. Now, management, this is a management decision. Management says, okay, tell you what, John, I'm doing this project. So, okay, tell you what, John, I'm willing to take a 2.28% risk. I like that because it makes the math easy, because that puts it right at 2 sigma. How do I know that? Well, I just looked up 2 sigma in the Z table, 2.00, and it's 0.0228, and that is it. So that makes it easy for my math, because I know I'm always need to be 2 sigma out to reach my 2.28% risk. So this is a management decision. This is the risk they said they're willing to take. Now, let's look at this and say that this is all I have in inventory, or this is all I get is 100 pieces per day. Half the time that'll be good enough, half the time it won't. But if I start out, it will work, by the way. That scenario will work if I just get the average every day, as long as this is what happens. Day 1, I'm below the 100 pieces. So I build up a little bit of safety stock or inventory. So I'm okay. The next day it increases above, but only the same amount that it was below the day before. So now I'm at 0. I used up all my excess inventory. As long as it always went like this function here, I would be okay. I would be great shape. The problem is, if you have my experience in life, you're not going to be that lucky. And it's usually going to look like this. Okay, day 1, darn, we don't have enough material to meet demand. Day 2 is even higher. Oh no. Day 3, even higher. Or still above average, I should say. So I'm getting further and further behind on meeting customer demand. Day 4 is still above. Now I'm in trouble. Everyone's yelling at me. I'm threatened to be fired, etc. Personified blame and punish is in full effect. And finally, day 5, I make it below. And so I can make up lost ground, but I've already got a bad name for myself. Why? Because I'm taking a 50% risk, and that's going to come back and bite you all the time. So you say, okay, how much more inventory do I need to survive in this realistic environment? And so there's a probability that, what's the probability that I'd be above that? You can come over here and add that area up above there and see what the risk is, etc. We oftentimes call sigma, by the way, uncertainty, especially when we're talking about demand and variability, etc. Okay, so let's go back and say, okay, I'm willing to take a 2.28% risk. I'm currently getting 100 pieces per day in every day. But how many more do I need? How many more pieces do I need to do 2.28%? We call it safety stock, by the way. Okay, well, I need to go out 2 sigma, so what's the difference? I'm getting 100 every day, but I need another 20 to support the risk. So now I'm no longer, if I'd put 20 additional pieces in safety stock, all of a sudden, bang, I'm not in, I went from 50% risk to 2.28% risk, which is what the management said they were willing to take. So we're in pretty good shape here with just 20 additional pieces. So I'd order 20, but I wouldn't order 120 every day. I'd order 20 a day. I'd put 20 in safety stock. Then I'd go look at the safety stock every day, and if it drops below 20, I would add more orders to for the following day to try to keep that at 20 pieces of safety stock. Every day my goal is to have 20. Of course, that's going to fluctuate a little bit, but that's the goal, is to order extra every day above the 100 to try to maintain my safety stock. And if I do that, I've dropped from 50% risk to 2.28% risk. But before I say just 20, let's look at the rest. If we assume a worst case of 4 consecutive days above average, then you will have to multiply the 20 pieces of inventory by 4. So I'm going to assume, hey, I could have 4 consecutive days above average. And you could. Of course, you're more likely to get half and half, but it may go, and it's not unusual to have 4 above, then it finally drops below. So you may create your own assumption for your project, but for this make-believe project, I'm going to assume 4. So to be safe, I'm going to multiply the 4 times 20. So the inventory to protect against uncertainty, the safety stock, at the 2.28% risk level, I must hold 80 pieces of inventory. So now that's my new safety stock is 80 pieces of inventory. And that should help me out a lot. That's covering all my risks, and I'm being a little conservative with that 4. So if it's not real expensive, I'll probably go ahead and go with that 4-day assumption. If inventory is really difficult to come by and very expensive, maybe I'll take a little more risk and drop that down to 2 or 3 days. So under these conditions, we need 80 pieces of safety stock or inventory to protect us against this uncertainty. However, this is not the only uncertainty in the supply chain. Other forms of uncertainty include administrative lead time and production lead time. Okay, let's define that. Administrative lead time in this discussion means the time it takes purchasing to order a part from a supplier after the part has been requested internally. So the manufacturing people say, I need this many parts, and it takes purchasing on average so many days. And of course then there's going to be variability in those days because they have different workloads, etc. Production lead time in this discussion means the time it takes from the time the order from purchasing is received by the supplier to the time the order is delivered to the purchasing organization. Of course, each of these lead times have uncertainty, which we call sigma. Okay, so now we've already talked about demand. We've decided for demand variability we need 80 pieces. But what about administrative lead time? How many pieces? The difference is over here we were working with the number of parts. Over here we're working with time. So it's a little bit different. But remember, for every day we wanted to have what? 20. That's what I'm going to assume anyway, is that every day I need safety stock of 20 to maintain my 2.28%. So keep that in mind, 20 a day. So if this takes so many days, I'm going to multiply the number of days by 20 to calculate my safety stock requirements for administrative lead time. Then of course production lead time will do the same thing there, but it's going to be a time. Both of these are time elements, so they're going to be a little bit different, but they're not bad. Remember, I did say this was a 9. It is rather complex, so if you feel a little lost, this may not be the project for you right now, but we'll go through it anyway. Now we will discuss the concepts used in calculating required inventory levels for administrative lead time and production lead time. So I'm going to give you my assumptions on how I do it, and you may come up with better assumptions. If so, that's a good thing. You always want to improve upon things. But this will definitely get you thinking. So now I know as a production person that I need to, on average, put in my required needs 3 days before I make the part so that the administrative people will have time to submit my order to the supplier. I know that's one of the things I need to take into account. So because of that, I'm going to assume that I always add an extra 3 days. An extra 3 days to administrative lead time. So I put it in, my order in 3 days before I know I'm going to need it as far as administrative lead time is concerned. Now, however, there's variability in that. Sometimes purchasing will do it in 3 days, but sometimes they do it less, and sometimes it takes them longer. So you have to keep track of this time, and usually you do it with barcoding is the best way of doing it. So they have paperwork, and they get it, you put it in, they run it through the barcode, says time starts here, and then when they place the order, they run it through again, and it calculates the number of days that took. And from there, you can calculate sigma. Okay? And of course, you're not going to have, you may do this 30 times to get enough data to calculate that number. But it takes 0.5 days, so I fill it out. 3 plus 1 sigma is, and sigma is 0.5, so that's going to be 3.5, 4, and 4.5. This is going to be 3, 2.5, 2, and 1.5. Okay, so I got this all filled out now. And remember, we're willing to take what? A 2.28% risk per management. Well, let's look on, I put it in on 3 days anyway, 3 days before I need it. We've got that under control, so I don't need to worry about that. But this uncertainty is another extra day. Another extra day. And how many inventories did I say I'm going to assume a day? 20. Remember that? 20 to take care of the uncertainty. So I'm going to have to add another 20 pieces of inventory to my safety stock to take into account administrative lead time. And you can also calculate how much that's costing you, which we'll do in inventory costs. So you can let everyone know your variability is costing the company this much in excess inventory. And if you could reduce variability, it would cost less money. That's where we're getting at here. Okay, now production lead time. So the administration, purchasing people put in the order, and on average it takes 40 days. So now you have to, on average, order things 43 days before you need them. 3 for administrative issues, and once the manufacturer gets your order, on average it takes them 40 days to turn it. So 43 days, you know that, you turn it in. That's what I'm assuming, that when you need something, you order it 43 days before you need it. But there's still this uncertainty going on, and Sigma is 10 days for this from your supplier. So that makes this 40, 50, 60, 70, and of course 40, 30, 20, and 10. Okay, and we want to go out 2 sigmas to get our 2.28%. So what is that? 40 to 60 is 20 additional days. 20 additional days times 20 pieces per day means that for my production lead time, it's going to take 400 pieces of inventory. And so this is also nice in that purchasing can say, well, that costs a lot of money in inventory. Maybe I should look for a supplier that's better at reducing variability in delivery times, because that could save us a lot of money. Right now, no one even thinks that way. So this is a huge, strategically important project. And I wish more people would do it. It could change your company. It really could. So anyway, I've determined that for demand uncertainty, I need 80 pieces of inventory for the 2.28% risk. That's going to cost me $200 per part. So 200 times 80 gives me $16,000 that demand uncertainty is costing me in inventory. And then $4,000 for administrative, because remember that was 1 day, 20 pieces per day. So 20 times 200 gives me 4,000. And this one is the big one, 40,000 pieces, or 400 pieces of inventory times 200 gives me $80,000. I add that all up, and it costs $100,000 worth of inventory to support my uncertainty needs. So hopefully that made sense. You may need to listen to it more than once, but this isn't the end of it, of course. Now you need to figure out, how do I reduce the need for inventory? Well, demand is probably the most difficult one, but reducing variability in time is actually a fairly easy project. So now we understand our current state. How do we reduce inventory costs without violating our standard risk? The answer to this question is to reduce supply chain variability. By the way, I did have a student that did this corporate-wide in this huge corporation that has probably around 200,000 employees, and their inventory costs were like billions, okay, in the billions of dollars. And so he did this project, and at the end of every year they'd have these competitions of who came up with the best project and saved the company the most money, and which company was strategically the most important. And they gave the person, whoever did the project, $10,000, a lot of recognition, which equates to promotions in your future, most likely. And they did this when it took the #1 position. It took the #1 position, took first place in all the from all the projects in this corporation. So very, very powerful project that can save your company huge amounts of money. So here is what I've done, is I've used the administrative lead time, 0.5 days. It was 3 days average, I think. Yeah, it was. And we go out 2 sigma, and there were 20 pieces. So I actually drew 20 pieces in here to scale, so you could see, learn what I'm about to teach you. So that's 20 pieces of inventory to get my 2.28% risk. But what if I reduce variability in time through the administrative process? Now 2.28%, since sigma is smaller, is over here, and you draw it up there. This was the current best practice before you reduce variability. I can get rid of that inventory while maintaining the same risk. So now you understand something that hardly anyone does, that the need for inventory comes from variability in your process, variability in time and variability in demand. That is very powerful. I hope you never forget that, and I hope you implement this. Okay, so I was able to reduce, how many did I cut out of there? One, I have to count, I think I counted over here. Capable of removing 5 pieces of inventory while maintaining the standard risk due to reducing variation, solution 3. So now I can come back and say, okay, I did a project, so now we only need $3,000 worth of inventory. Now we must ask the question, how do you reduce variability? Well, first, there are many methods that can reduce variability. Which method is used depends on the type of variability. One of the methodologies that can be used to reduce variability in time, such as administrative lead time and production lead time, is a methodology referred to as lean. So you guys are going to have some lean modules in here. So now you could go do a lean event. What is lean? Lean is waste. And waste in processes create variability. The reason for variability is waste. If you have zero waste, you have zero variability. I'd say it's a direct correlation. This lean methodology's main objective is to reduce waste from the process. The lean methodology has its roots in the Toyota production system. When you take waste out of the processes, then variability in time goes down. So in summary, if you want to reduce time, variation in administrative lead time or production lead time, you must take waste out of the process as suggested by the lean methodology. And the next best good question, logical question would be is, well, what is waste? Well, here is waste. Overprocessing, transportation, motion, inventory, waiting time, defect, and overproduction. Now I'm not going to define each one of these here, but when you get into the lean part of this class, they'll go into great detail what each of these means, and you need to go work on those. Maybe administrative lead time, they put it on the desk and it sits there for 3 days. That's not good. So you need to find out why is it sitting here and fix that problem. When you do and you reduce waiting time, variability goes down. That's how you do it. This is not a difficult thing. At least academically, lean is very easy. Sometimes implementing it can be a little tough. Remember, you have to have a culture to support these tools. If you have the culture, these are not difficult projects in most cases. So you have a lean project. So let's say you do that and you reduce variability in production lead time and you save some more money. It was $80,000 for the 2.28% risk. Now it's $64,000. So now where are we at? $3,000 needed for inventory to support supply chain uncertainty now. And so you saved, what is that, 17 or 18,000, whatever it is. So that was pretty good. Now the question is, the more difficult one, how do you reduce variability in demand? And it's strategically important that you know that one way of doing this is, and that looks like it got cut off a little bit. Not sure why that is. But let's pull up another shot here to just take care of that. There we go. And let's see if this helps us a little bit. Not a lot. I'm not sure what's going on with that. That didn't help at all. So anyway, it doesn't matter. So what you have is market diversification is how you reduce variability in demand. So, for example, I had a client, they sold something for the oil drilling rigs. And oil, the problem with oil is oil prices is up and down, and about that time they came up with shale technology to get oil out of shale. So there was this glut of oil in the market and demand just dropped for their particular product. And then eventually it'll come back up, but it's a pretty radical move. Well, if they could diversify and go into other markets, sometimes when oil's down, other markets are up. So you go pick a market and you focus on that, and you diversify your portfolio, and that smooths out the demand. And that's a strategic thing that upper management has to look at and say, listen, this is too much variability in demand. let's keep this industry in the oil industry, but let's go into the machining industry also, and maybe the aircraft industry, whatever. And all of a sudden, since you have a diversification in who you serve as a customer, it smooths out the demand, variability goes down, and your need for inventory goes down. Okay, another thing you can do, and I know some people don't like forecasting, and I don't either. If you don't have to do it, you shouldn't. But sometimes you do. If you can reduce uncertainty in forecasting, reduce variability in forecasting, you can reduce the need for inventory. Now that's a whole nother project, and I have a project. For those of you that are maybe students doing this and they don't want an academic certificate, you want the full-blown certificate, I have a project where you can do forecasting, and you can get someone's demand data, and then you can try to forecast it. And you can get that off the internet, so you don't have to be working at a factory. So if you're interested in doing that, let me know. It does take time. This is not necessarily an easy project. It's a very interesting project. But by reducing forecasting error, you can also reduce variability in demand. Okay, and reduce uncertainty. So let's say we've done that. We did better at our forecasting, and now we reduced it from 80 to 60 pieces. So there we've saved much more money. Now there were 79,000 needed for support of the 2.28% inventory risk. Okay, so a very powerful project. A lot of projects can spin out of this. You could really spend your whole career becoming an expert at managing inventory risk, reducing risk, and saving companies huge amounts of money. We had a student that they did this forecasting project that I told you about, and the reason they did it is because they got their forecasting from salespeople. Well, salespeople, just to survive, they have to be unrealistic optimists. Okay, that's just the way you have to be in sales. So they give them these huge numbers, and they built, I think, $365 million worth of inventory, and they couldn't sell it afterwards. It was a bad forecast. And then the customer changed the design, so they had all this inventory, $365 million that's basically just garbage, a waste of money. And so because of that, they said, let's try to do better at forecasting. So my student did the forecasting as I trained him to do, and it said if they would have used that forecasting technique instead of the one they did, it would have saved them around $300 million. Okay, that's a lot of money. Now, you may not be working with that big of a company, or you may, but there's huge amounts of money out there to be saved. So the problem so this is what a lot of companies do. They say, we're going to reduce inventory by 25%. Okay, so that's where we're at. So the problem of reducing inventory levels by 25%, so management said, we got to reduce it 25, they just cut it, while maintaining the standard risk has been achieved through the reduction of variation. This problem is solved in an objective manner. So all I did is summarize, this is what we've done. We've reduced the need for inventory by 25%. Sometimes, this is what I was kind of alluding to here, sometimes what you see companies do is demand a 25% reduction in inventory, which happens, but with an increase in risk. And then they're mad because they weren't able to meet their commitments, and then everyone gets punished as a result. That's not how you want to do it. You want to do the lean activities first, reduce variability in time, reduce the need for inventory by 25%, then cut inventory by 25%, and it takes you back to your standard. Congratulations, you have almost completed this module. However, remember, you still need to complete that module exam. If you have any questions, please contact me, and I'll get back with you as soon as I can. Congratulations, you have completed this module. I hope you have learned something new that will enhance your career. Thank you, and goodbye.